Hello and welcome to Add-on. So today we will learn about the band theory of solids. And the band theory of solids helps us explore and understand different materials, especially the N-type semiconductors and the P-type semiconductors. And along the way, we will look at how Fermi levels vary with temperature in these semiconductors. So let's start. So have you ever wondered why some materials are good conductors of electricity while others are insulators? Or why some semiconductors behave differently than the others? Well, the answer lies in this band theory or the theory of energy bands. So, imagine atoms in complete isolation. Each has a set of distinct energy levels for its electrons, but when we bring these atoms closer, like this, as in a solid, their outer or the valence electron starts to interact. Right? And this interaction splits each atom's energy levels into many closely spaced levels. And these levels form energy bands, where electrons can move around freely. So what exactly is this energy band? So in solids, the original discrete energy levels become bands of allowed energies, and these bands can support the movement of electrons. So electrons will be moving here, right? So to understand the band theory better, let's look at the few postulates it has. So the first is continuous and forbidden energy levels. So what are these? Well, electrons are allowed to settle in specific energy bands, but there are forbidden gaps between them. Now, what are these forbidden gaps? So forbidden gaps are the gaps where the electrons cannot exist. They are forbidden. And the next comes inner versus the valence electrons. So as electrons come closer together, the inner electrons are less affected by their neighboring atoms. But the valence electrons, which are the outermost electrons, these interactions change the valence electrons' energy levels significantly, creating broad energy levels. We can see this in the diagram here, but we will understand this diagram later. Now the next point is the capacity. Capacity of energy bands. Now, what do we mean by capacity? Well, in a solid with n atoms, each energy band can hold up to 2n electrons. That's because each energy level can hold 2 electrons, one with spin up and one with spin down. Right. Now the next point is valence and conduction band. So what are valence and conduction bands? Well, valence and conduction band are the two crucial bands in any solids, and the valence band is filled with electrons that hold the structure together, and the conduction band lies just above the valence band, and electrons in this band are free to move and conduct electricity. But the valence band is completely filled. Now, what do you think happens if there is a wide gap between the two gaps? So, if there is a gap between the valence and the conduction band, like in insulators, electrons cannot easily move to the conduction band. However, if the gap is narrow, like suppose this is the conduction band and conduction, suppose the valence band is completely filled with electrons. So, if the gap is narrow, as in semiconductors, they can jump to the conduction band with little external energy like heat. Now, let's discuss the Fermi level. What is this Fermi level? So, Fermi level is an imaginary level that helps us understand electron distribution. So, in case of metals, the Fermi level lies within the conduction band because these materials conduct electricity easily. So, let's understand this with the help of this diagram. So, in this diagram, we have this for the metal. So, in case of metal, there is an overlap between the conduction band and the valence band. So, which helps in what? This helps the metals to conduct electricity more easily, right? So now let's understand this for the semiconductors. In semiconductors, the Fermi level lies somewhere between the valence and the conduction band, and its position changes depending on the type of doping. And in case of insulators, the Fermi level is far below the conduction band, and this is the band gap, and the band gap is largest in case of insulators. Band gap. Now, what is mean by doping? Well, when we add impurities to pure semiconductors, a process called doping is needed, which creates either N-type semiconductor or P-type semiconductor. Now, N-type semiconductors has extra electrons. So the Fermi level moves closer to the conduction band because there are more electrons available for conduction. But in case of P-type semiconductors has holes or missing electrons, which act like positive charges. So the Fermi level in case of P-type semiconductor shifts closer to the valence band. So how does temperature affect Fermi level? So in both N-type and P-type semiconductors, as temperature increases, the Fermi level shifts slightly. And for N-type, it shifts downwards towards the center. And for P-type, it moves upwards. This changes because higher temperature excites more electrons across the gap, making their distribution even more distributed evenly. So as the temperature increases, electrons gain energy and jumps across this gap. In both N-type and P-type semiconductors, the Fermi levels begin to move closer to the intrinsic level, which is near the middle of the gap, creating a balanced distribution of electrons and holes. So why do you think semiconductors are so valuable in electronics? Because their electrical properties can be controlled with proper doping and temperature, making them ideal for switches and amplifiers and in devices like that, and also in our computers and smartphones and so on. So let's quickly recap. So in a solid, atoms are packed close together, causing the energy levels of the outer, which is the valence, electrons to split and form energy bands. And these bands allow electrons to move around depending on the material. And energy bands have gap called as forbidden gaps where electrons cannot exist. After that, we learned that the valence band hold electrons that are tightly bound, while the conduction band can host free moving electrons. And after that, we learned that insulators have a large band gap with no easy movement, whereas metals have overlapping bands, making them great conductors. And semiconductors have small gaps allowing electron flow with slight excitation. And after that, we learned Fermi level. And what is Fermi level? Well, the Fermi level indicates where the highest electron energies are in a metal. Its position in metal is given by this diagram, in which due to the overlapping of the conduction and the valence band, the Fermi level lies within the conduction band. In case of insulators, it's far below the conduction band. And in semiconductors, it sits between the valence and the conduction band, depending on the type of doping. Then we learned about doping. N-type. In case of N-type, Fermi level is closer to the conduction band. In case of P-type, Fermi level is closer to the valence band. And as temperature rises, the Fermi level in both N-type and P-type semiconductors shift towards the middle, balancing electron and hole populations. So that's all for today. Thank you for watching.